Hi everyone, today we'll be discussing persistent memory and database indexing. As an overview of what we will be discussing, first we provide background knowledge about persistent memory technology and the techniques that are used to implement persistent data indexing structures. Then we will talk about the goals of our research, evaluations, and analysis. Next, we explain the technologies and techniques in more depth. We will then explain how we evaluated the indexing structures and provide the results. In the fifth section, we analyze the results and provide insight into the benefits and drawbacks of persistent trees that we have evaluated. Finally, we conclude with the applicability of these technologies, as well as the future of persistent memory and persistent indexing trees. So here we have some background information. The data storage hierarchy, as it stands today, has the CPU registers, caches or SRAM, and main memory such as DRAM in the top three tiers. The closer these memory devices are to the top of the hierarchy, the faster they are, but also the smaller and the costlier their storage is. With modern technology, the top three tiers are all volatile, meaning that the data stored in them does not persist without power. As we move down the hierarchy to flash memory such as solid-state devices and magnetic disks, the memory mediums become slower, cheaper per byte, and have higher storage capacities. These two memory devices are commonly used non-volatile storage devices. Storage class memory, or more generally, persistent memory, is an emerging class of memory that offers efficiency comparable to DRAM, reduced power consumption, better granularity, and most importantly, non-volatility. Databases and database indexing heavily depend on the different levels of memory to work efficiently and provide sound data consistency. There are several B+ tree variations that leverage the capabilities of persistent memory to improve database indexing as we know it. So now we'll discuss some of the novel persistent memory technologies. The first persistent memory technology is phase change memory, or PCM for short. It is just one of the many persistent memory technologies that promises read latency, write latency, and write endurance superior to flash memory, non-volatility, DRAM-like density, and byte addressability. Resistive random access memory, or ReRAM, offers similar properties to PCM by combining the properties of electronics and electrochemicals. Spin-torque magnetic RAM uses magnetic memory technology to offer these advanced persistent memory properties. Finally, we have MEM resistors. Developed by the National Energy Technology Laboratory, it is a simple and small structure that is versatile and is used in creating memory technologies that have similar qualities to the upper tiers of the memory hierarchy while offering the non-volatility of the lower tiers. The three B+ tree indexing structures we will discuss are the fingerprinting persistent tree, or FP tree, proposed by Oak et al., the BZ tree, proposed by Larson and colleagues, as well as the right atomic B+ tree developed by Chen and Jin. These are not the only persistent B+ tree designs that have been created or proposed. However, they are the ones we discuss in this presentation because of their prominence in the persistent indexing area. We will elaborate on these trees in the Techniques and Technologies section.
Thank you. We're going to be talking about goals now. So an issue faced with the current data storage hierarchy is main memory being volatile. So that means that if power is lost, so is the data. Therefore, the only affordable and persistent place to store data is disk memory. but retrieval of data from there is slow, and consequently that reduces performance. Currently, the most common example of persistent memory is flash memory. Unlike newer technologies such as phase change memory, its performance is nowhere near DRAM. It is also located outside the system. Comparing current memory technologies and new persistent memory technologies is a topic we will be discussing further throughout our research. New persistent memory innovations have demonstrated performances similar to that of DRAM, but with much higher capacity. This creates a large gap between PM technology and disk storage. These new technologies consume significantly less idle power, are non-volatile, and can be used in place of DRAM. We will be discussing the future of persistent memory database indexing structures, the feasibility of attaining universal memory, hybrid PM-DRAM systems, and changes that need to be made to our current data index system to function with persistent memory. We will be discussing the benefits and challenges with persistent memory indexing and identifying which of the index structures FP tree, WB tree, and BZ tree perform the best. So the design principles of persistent B+ tree indexing techniques are persistence, near DRAM performance, robust performance, fast recovery, and high scalability. We're going to be talking about technologies and techniques now. So the first tree that we're going to talk about is the fingerprinting persistent tree, FP tree for short. This is a combination of PM and DRAM that reaches similar performance to DRAM-based equivalents. So as you can see in the graph, FP tree uses a technique called selective persistence, where it stores inner nodes in DRAM and leaf nodes in persistent memory. Compared to transient data structures, leaf node access is slightly more expensive, but FP trees allow for fast inner node lookup while simultaneously maintaining data persistence. The benefits of storing leaf nodes in persistent memory is that it allows inner nodes to be rebuilt in case there is a crash. That is why the tree is persistent. This results in FP trees having a great runtime performance but slow recovery time. Since FP trees have both a transient and a persistent part, different concurrency control methods are used for each. Hardware transactional memory is used for inner nodes, and fine-grained locks are used for leaf nodes.
For the second method of implementing a memory persistent B+ tree indexing structure, we look at the BZ tree. The BZ tree is a lock-free B+ tree. Lock-free index structures maximize the performance of parallelism and are used by modern CPUs and main memory databases. BZ trees use persistent multi-word compare and swap, or PMWCAS, which automatically changes multiple 8-byte words with persistence guaranteed. This means that either all specified updates succeed or none of them do. In the BZ tree structure, internal nodes store the search keys and pointers to the child nodes, while leaf nodes store keys and either record pointers or actual values. BZ trees use the standard atomic key value operations, which insert, read, update, delete, and range scan. Overall, the BZ tree is a high-performance latch-free index that has reduced complexity due to the use of PMWCAS. That can also be used with either DRAM or persistent memory, which is a huge benefit for testing, as persistent memory is still in its infancy.
Hi, so now I'll talk about the right atomic B+ tree. Recall, a fingerprinting persistent tree stores inner nodes in DRAM and leaf nodes in the persistent memory. WB tree stores the entire tree in persistent memory, so it might suffer longer lookup time but shorter recovery time. Unlike traditional B+ trees which have sorted nodes, WB tree actually keeps its nodes unsorted to reduce write cost. So when a new key is inserted, we don't have to shift the data. However, a linear search for lookups is required. Well, how do we improve this? To solve the problem, WB tree uses an in-direction slot array where each entry of the slot array holds the index of the corresponding key in sorted order. So this will enable binary search just like traditional B+ trees. The WB tree also uses a bitmap to indicate whether a slot entry contains a valid record. Both the bitmap and indirection slot array are used for reconstruction and recovery upon crash to make the tree persistent. Finally, this WB tree is a single-threaded tree, so all concurrency problems are avoided.
Now I will walk through the evaluations of the indexing structures. Here we have the first evaluation results for the trees. In this bar graph, we have plotted the throughput in millions of operations per second for each of the trees. The operations are quality search, insert, update, delete, and range search. The green bars represent the performance of the FP tree for each operation, while the blue bars represent the WB tree and the orange bars represent the BZ tree. In the second evaluation, there is a separate bar graph for each of the tree operations. The operations are the same as in the last evaluation. This is a measure of the kilobytes per operation that is used. The different colors on the graphs represent the different types of storage, green being DRAM, blue being persistent memory, and red and orange represent the device reads and writes. Several of the persistent memory writing accesses are much higher than the graph. We had added the numbers above. You can see these ones here. Now I will analyze the results found in the evaluations. Here we have the average throughput for all of the trees across all of the operations. As we see on this slide, the FP tree outperforms the WB tree and the BZ tree for almost all operations, except for the range search, where the WB tree performs the best. On average, the FP tree performs approximately 460,000 operations per second, which is nearly 1.4 times faster than the WB tree and 2.4 times faster than the BZ tree. This is mainly because the FP tree is a hybrid of DRAM and persistent memory, while the other two trees are persistent memory only. At this stage in the development of persistent memory technologies, this output is to be expected. As persistent memory technology matures, the performance gap we see here will close, and ideally, the persistent memory only solutions will provide better results than the alternatives. In this analysis, we only mention throughput because, as it mentions on the slide, it is basically the efficiency of database operations. Later on, we will discuss some other important measures. Now let's discuss these results. Cross-reference other research and some of the additional metrics they had analyzed in their reports are execution time, tail latency, last level cache misses, number of cache line flushes, and the recoverability. These additional metrics, while significant, are often used to support the general analysis of throughput, and we wanted to focus our analysis on the performance based on throughput. The table shows the recovery times for the trees after 50 million and 100 million record inserts. The recovery time for the index structures that only use persistent memory, like the WB tree and the BZ tree, is much faster than the other indexing structures, like the FP tree, which are a hybrid of DRAM and persistent memory. So, the trade-off is worse overall performance for faster recovery.
Alright, so to conclude, with the ongoing development of persistent memory, the memory hierarchy, as well as the data indexing and file organization techniques, may be revolutionized in the foreseeable future. The B+ tree designs described and evaluated in this paper have different use cases, as the recoverability of PM-only trees drastically outperforms the PM-DRAM hybrids, that is the FP tree, although the throughput of FP trees is much better for all operations. There is no clear winner between these PM trees, as all of them will play a huge role in shaping the future of database indexing. One of the main goals of persistent memory as it applies to databases and database indexing is rapid recovery. We can conclude that recoverability performance is superior to that of the traditional solutions because PM technologies are designed to be high-performing and non-volatile, and our evaluations confirm this feature. That is the end of our presentation. Thank you, everyone.